So my name is Claudius Isilescu, and I will present what Oracle team did for, or does, is still in progress, for enabling MTE extension, ARM64 MTE extension for the toolchain. A short overview, I will talk a bit about what is, why we need MTE, and then I will go briefly to see what are the progresses in binutils, glibc, and GCC. A small example, and then, yeah, I would not say conclusions, but I would say work in progress. So we have a big problem, with C++ memory safety. This is the problem why, Rust is kicking in. So one of those problems are, like use after free, buffer overflow, uninitialized memory. There's also some security vulnerabilities. A solution for this, which is proposed for ages, is, of course, memory sanitizers. Yeah? So we have a software implementation also on GCC, in LLVM as well. But the software implementation comes with some penalties, of course, like big CPU overhead, the code size is bloating, the RAM is also used, it's quite large. So then we got the hardware-assisted address sanitizer. Yeah. So the idea here is to use a tag within the address, with 8-bit tag in the upper bit. And this tag will be valid for a 16-bit byte memory granule. Yeah? So I think there are 3 architectures at this moment which are supporting this kind of memory tagging. One is AR64 via the top byte ignore. So this is quite old, I think, feature.
Part of the architecture originally.
Yeah, I think it is.
ARM
So then we have the x86, this linear address masking. I don't think that it's used in GCC. It is there. It's
there.
And
you have to have the hardware to do it.
Yeah, and then I think the Spark, I think Spark has something similar for the memory tag. Yeah. So I apologize for the Spark. I forgot to add it.
Which is funny.
So I will just, I'm trying to explain a bit here for the guys which are not knowing what memory tagging is. Basically, you have a large address and you reserve the top byte for the tag. Yeah. So you have an allocation tag, which is it's tagging a zone of memory. It's granule, let's call it. And we have an address tag, which comes to the pointer. So whenever you want to address that piece of memory, the tags are compared. And if they are not OK, an exception is generated. Now, even with hardware-assisted sanitizer, you have to generate the tag, you have to shift it, you have to insert it in the address, and you have to extract it if you want to compare it, to make the compare and to generate the exception. So it's a lot of work here. And this work has been addressed by ARM with the memory tagging extension. So memory tagging extension comes with a 4-bit allocation tag. It's not 8-bit like in let's call it more software version. And it's working on 16-byte granule. Yeah. It adds a number of instructions to manipulate the tag. And we hope, or also probably ARM thinks the same, that will have a low overhead in the range of a single-digit %. Yeah. Compared with twice or 3 times the memory. And, there are plenty of instructions there. I just choose the one which I'm using right now. We are using for a GC patch. It's a selected one. This is this IRG, which is important because this is basically generating a tag ADG sub G is for tag manipulation, let's call it like that. STG and S2G is for storing the tag. We have has also the loading, so you can load. And GMI, it's basically manipulating what tag you want to take out of the random pool. So I'm using it to try to generate unique tags. Of course, there it's a 4-bit tag. This means 15 useful values. So coming back to the picture, this is changing a bit. I'm trying to show that those instructions are changing a bit the operations. So we don't need to do too much extraction insertion. IRG GMI will generate the tag. STG will just directly put it. It works on the upper bits, directly tags the memory. And you'll get the comparison and of the tags via normal LDR, STR type of load store type of operations. Yeah, so this simplifies a lot your problem. So narrow the overhead. Here it's let's say a small example what kind of bug we aim to discover with MTE. This here it will have buffer overflow underflow. I have an alloca of 20 elements, so this means 2 granules. And if we ask something, we have a buffer overflow, so we ask something from 20 to 31, this is not detected because it's in the same granule. Yeah. If we access position 32, we have clearly an overflow. This is detected because it's outside of the granules, and it's roughly 93% detection rate. An underflow has the same detection rate. Yeah. So let me go quickly to the code because it's a bit more easier. It's the same program, and you can see here that I'm generating with IRG the tag. This tag x0, it's an x0, register x0, and is stored in the memory with ST2G because there are 2 granules, it's an optimization. And then each time when you do the store, the MTE hardware will check for the tags. So it will check if the allocation tag is equal with the address tag. Yeah, address tag, you see it's in x0. So each store will use the address tag, which is in the upper bits of x0. So the first store, it will not be detected the same granule. The second store, it will detect the exception. It will detect the 2 different tags because that 32 it's outside of the tagging space, and will give me an exception. If you reach the last one, then it's a problem, but usually you get an exception to the first one. We have some overhead, looking to the MTE, we will have some overhead in generating, fetching memory tag, initializing. As you could see, we have the GMI, IRG instructions, sub-G, add-G instructions. Also, we have, probably for a malloc, we have a number of O-size more operations. Yeah, so we have this is what we estimate. A stack for a stack object, we also estimate a O-frame size, more instructions. Also, we have a problem that the granule has to be aligned. So we have also a constraint there that will increase the stack size. And yeah, then we have also the extra code size via the tag and untag procedures, and using for each stack variable, you use its own with your register, yeah, with your variable. So that will increase everything. So how things will work? This is, let's say, like an overview. Of course, everything it will be done in the GCC compiler, in the sanitizer there, in hardware sanitizer, hardware-assisted sanitizer. The assembler will annotate the dwarf that we have the MTE enable and the dynamic section that we have MTE enable. And glibc will take care of setting up the running environment, because we want to have to check if the hardware that has the MTE and then to enable it, and yeah. So I will go through all those tools, see what we did there or what is the status there. In binutils, we already have there the support. Indu is and Jose, which is not here, are the main contributors. For LD, we added 2 new flags. One is to instruct if what is the mtag mode, if it's asynchronous or synchronous. And the other one is to tell that, okay, we have a memory tagging, stack tagging tag in progress here. Yeah. So GNU assembler, the GNU assembler will take care of augmenting the dwarf with the G, with the string G, to indicate that we have the MTE tagging in place. We have introduces the CFI MTE tag frame directive. That directive is generated by the compiler, and the assembler will interpret it and will generate the G string. And of course, the readdref is modified to reflect the 2 new tags in the dynamic section. Yeah, from the LD. In glibc, it's again, does very simple thing. I already said it's a work in progress done by Cooper. I think you will do it whenever you. So it's still there. We need to improve it, I think. So basically, it checks for the dynamic tags and checks if the hardware can do something, and if so, enables the exceptions, and yeah, probably we get something there. In GCC, this work has been started by Indu. It's continued by me. So we added a new fsanitize option. It's memtag stack, which is basically using the hardware sanitizer, assisted sanitizer, to bootstrap and to generate the MTE instructions. Yeah. We have a number of patches in the. It's not fully upstream. A number of patches is still there, and the mailing list. And let's see what it's about. So introduces 2 target instructions. One is tag memory. Basically, this is tagging a memory. It's using the STG instructions in a loop, or unroll the loop if the size is not so large. And other instruction is compose tag. Compose tag basically tries to manipulate the tags without extracting them and putting them back in the address. So usually they use the ADG sub G instruction. Yeah. For the test which we added like 300 tests. We have 2 new predicates. It's arc64 MTE, which checks if we have the MTE support, and memtag exec, which checks if I can execute the test on the current platform. Yeah, so that is there. Here it's a bit of an example. Let's see how to use a toolchain. Of course, we have to pass the fsanitize memtag. The architecture has to support the memtag, otherwise you will not get anything. Once you compile, you can check if memtag was working, by checking for those two new tags in the dynamic. Yeah. Here it's a simple example. Let's go a bit through. The GMI there is used to guarantee the unicity of the tag. You might ask why you need there, because you might have only this GMI IRG, so the insertion of the tag is called many times, so there might be many times calling this, let's say, generate a new tag. So then I choose to use GMI. We can remove it if you think that it's an overhead. Yeah. The sub G is, as you can see, is manipulating the pointer. So basically, it's adding 16 bits to bytes to X1 register. The tag is not modified. So probably here, I do not know. That's the question. Yes.
If you keep in the GMI and make the tag unique, then you get 100% detection on linear overflow, right? Because the tag changes at the boundary before things go really wrong.
You cannot have 100% detection, I think.
I think perhaps
If
I think you could push it up a little. At the moment, you can always detect underflow, but it only detects overflow once you pass the granule boundary.
Yes.
It's quite a long way away. If you move local variables, possibly malloc return value pointers, so that they're as close to the top of a granule as a natural.
Yeah, I mean, you could pad it in production as well, and then count.
You couldn't overwrite the next variable after it. You would always spot that.
Yeah, exactly.
Yeah, you can do that.
Maybe it doesn't potentially impractical, but it seems possible.
Do you force every single
Yeah,
local variable to a different variable?
yes. So this is a single example. Let's go for the. So what I wanted to say is, please remark that before exit, I have to clean the tags. Yeah, to make sure that I don't have any trash there. Yeah. So for multiple variables, yeah, I have for each of them a tag. Yeah. I use sub G. You can use the IRG. It's the same thing. So each time, so of course, having 14, 15 tags, if you have too many variables on the stack, you might have chance not to, or you might have a chance to have false errors.
You'd be very unlucky if you're doing have a massive array and hit it just.
Can be a structure. Can be a structure. Yeah, I would know. Yeah, I would know. Does it work? Yeah. So this is somehow the status of GCC, which is in the patches in the move right now. The next thing which I'm thinking to add is using the STGP instruction. STGP instruction is kind of a super instruction which combines the setting of the tag and writing the memory with the data. So that is something which will reduce the overhead in the compiler. Probably Cooper wants to add the malloc. Shoot me if I wrote something. Okay, yeah.
It's not really great. I mean, the current implementation in glibc increases the chunk header size to 16 bytes, so it has a distinct granule and can be tagged differently. And that's not really great because it means that your workload suddenly needs a bit more memory.
Yeah.
And depending on what you're doing, that can really impact performance negatively.
So you think that is not worth it to be allowed?
I mean, we are looking for better implementation so that you can actually turn it on in production, but
Okay.
today it's just not there.
Okay.
Yeah.
There's nothing that can be done about it now in the sense that it is a hardware requirement that the granule the tag is put on the granule, right?
Yeah, I mean, the issue is particularly noticeable for smaller locations, but there is no inherent guarantee that malloc has to have a chunk header in front of each relocation.
Yeah.
So if I don't know if there's still bits available with TBI, you could use the extra bit says this is a tightly packed arena where I don't have chunk headers, and then you use some other mechanism to locate the metadata.
Yeah.
And that would be, you could tag that onto glibc malloc. It wouldn't be nice, but it would be fairly
because
limited.
I think the ARM papers are saying that we should use it in malloc rather than, you know.
Yeah, but the glibc malloc implementation, I'm sure it works somehow, but it's more of a research prototype, I think.
Okay. We probably will have a stack unwinder issue in the presence of MTE. I'm still wrapping my head around that problem. Exceptions. You might land in a C++ exception. You might not clear all the tags, so that might be a problem. So I have to look into that problem as well. It was something said about stack protection using canary coloring, so using MTE to color the canary, and then you get when you get the stack smashing, you get the MTE kicking in. I'm not sure. GDB probably needs something. Again, I think
it's been done
it's
for a while
done.
now. Yeah. I was gonna ask if the stack MTE tagging is working correctly with GDB, because what GDB does, it looks at the mapping.
Okay.
There are mappings for the tagged regions, and then it goes and tries to present the right thing, present the tag numbers and things like that. So if you print a pointer, for instance, and it doesn't match the tag of the granule, then it will say so.
I haven't seen any problem at this moment.
Okay.
Yeah, so all my testing. I have a test which is a bit flaky, but it's something like it's working outside of GDB and the inside of GDB. So I'm trying to have an exception. So when executing outside the GDB step with QEMU, I have the exception. When I do inside of GDB, I don't have. So it might be because of QEMU and single step. But
okay. Yeah, because
GDB
was also patched to handle. I think it's like it's a SIG-SAG-V, but with the information about the memory tagging reason. Yeah.
So at this moment, I think it's working, the GDP. So this is the reason why I haven't added there. But seeing you here, it's worthwhile to ask. Some kind of summary. Like other sanitizer, it's a probabilistic method. So you might get false positive, false negatives, those kind of things. Some preliminary work has been pushed. Thank you, Richard.
He's not here. He's retired.
Maybe he will see the the presentation.
Yeah.
And yeah, we think that MTE, it's interesting because it offers a smaller overhead and also offers a high level compatibility with existing code. Of course, if you have some programs which are using the top byte, top byte to store something else, and this mem tag will store the 4 bits there, then of course it's not compatible. We need to do more compiler optimizations, but this should be after this patch, which is in the move, submitted, because there are a lot of things which are depending one of each other. So yeah, so I need some help to review the last GCC patches on this. So
You're looking at us three.
yeah, it was.
Two of us.
Yeah. We talk. Yeah.
Yeah. Because I don't know which ones are.
Yeah, I will just ping the patches. Yeah.
Yeah.
And that is it.
Or even where the latest ones are.
Yeah. Yes.
I can talk loud.
I know that you can talk.
Organic or electronic? Thank you. So in one of the slides, you actually said there are overheads of 50% to 100% to code size or performance.
Yeah.
Do you
For
have
the-
that statistics for
the
this
software,
method?
For the software one, yeah.
Yeah.
Yeah, it's a paper. I can write to me and I will send it to you.
Okay.
This one.
Yes.
Yeah, it's a paper, I think. And they analyze the standard software implementation where they say,
No, we're talking about the MTE method. How much?
So do
Oh,
you
then-
have something like this for the MTE?
for the MT, I haven't done this homework, so it's
Okay.
something which I have to do it.
Would be interesting to know.
Yeah, but it's definitely not in this.
Yeah.
It's
The
one
assembly
digit.
looked okay.
One digit %. Sorry?
Rambo head's going to be non-trivial. Yeah? There's going to be Rambo head on the stack. That's not going to be single digit.
Depends how much you use.
Well, it's every variable is 16 bytes apart from every other variable. That's
But yeah, if you have only a single variable, then yeah, the rest, it's, yeah. But can be.
yeah.
Yeah, it's anyhow, it's stack. Yeah, I said that because of this alignment, we have this increase of the stack size.
Just one thing, just to clarify, in the particular case of this MTE, there's no actually software implemented, it's everything hardware, so it's going to be a hardware implementation issue, and the performance would be based on that.
Yeah.
So it's not really under our control per se.
In theory, you could elect in theory, you could elect to not put every local variable in its own granule, but that would just worsen protection.
No, it will, yeah. Or you can color one frame with one color, and it's another. And if you go outside, this is basically a grip on the hardware sanitizer. The
frame with two colors because the return variable would always
Also, yeah.
So for MTE, are you using libason or not?
No.
That's nice because that's a security issue because the library is badly designed.
No.
And another question was if it's all or nothing. So if glibc compares that if all the libraries you load or DL open have the MTE support and only enable it if everything is, or if it can be the program and these few libraries have it. Or
Yeah,
the rest.
I think is that if you have just that program in the few libraries, then it will enable for those, isn't it? Cooper, for you it's the question. So when do you enable the MTE? You have the glibc, you have to be
if you have a library, one library loaded, or later on DL open a library which is not MTE enabled.
Yeah, so the plan would be to have a tunable, or there's already a tunable on this MTE. So either we reuse it, and then in my vision there should be some sort of a few options in this tunable that would allow to actually either enforce it for the libraries, either allow the libraries to not have MTE checking. I think as long as the code does not have doesn't use these instructions to set the granule, everything works fine.
Yeah.
So
the
there's
default is
a few options.
Zero. Yeah. Yes.
There are a few options.
Because we have this internal
similar to Intel Shadow
the
Stack.
tags. We know from
If you malloc in one library and the other.
yeah.
If I remember everything correct, sorry, I have to context switch because of
Yeah.
all the things. But so if the binary or shared library comes with this dynamic tag, then dynamic loader does the right thing by saying, okay, stack is now MTE colored, and now if the program uses these STG instructions and so on, things flow. But if then a shared library is loaded which does not have the dynamic tag, which means
That you don't have instructions, you don't have these instructions, and then the upper bit would be
which
zero.
is fine. So if the stack is still colored, it's still fine because they are not doing any checking.
Yeah,
So the
unless you
stack-
have, you do maybe unwinding and then things.
Yeah, so
Yeah,
this
so
is
that's
yeah,
what-
that,
that's
that-
one of the-
Unwinding is where things.
that is what I said, you know,
Yeah.
that I have to look in that unwinding.
So is it necessary for the stack to be left uncolored every time you,
I mean, it's obviously colored, right?
if you unwind?
Yeah.
No, so in the a function starts using local variables, it colors them, and suppose you have now a stack of all the execution stack of all these functions which did stack coloring, and stack unwinder now comes in picture, it has to roll back some of these stacks. Should the stack unwinder uncolor so that when you start executing again from a point and
Oh, yeah.
what you execute is not using MTE instructions, do you get false positives?
This sort of thing is why until shadow stacks is that everything must have a bit on or
So
nothing.
what do we do? What do we do in case of, say, software implementations of similar concepts? Do we uncolor every time there is a? We must be simulating something like unwinding there too. Do we uncolor when we do stack unwinding?
Even set jump. What about set jump, won't jump, and?
Same problem.
Same
Well,
problem.
no, that's what I'm asking. Is there, what does glibc do right now, if anything?
Nothing so far.
And swap context and.
For MTE.
Yeah.
For MTE.
Yeah,
so-
for MTE there is, I don't think
Okay.
there's anything.
Okay, so the issue is then that you call code that doesn't do stack tagging,
Yes.
and then it sees the checkerboard pattern in the tag on the stack, and it doesn't really work because it doesn't know about any of the tags and how they differ, and they just the code assumes they can just do an allocar and get something that has a single addressable byte range. Okay, I see it now.
Should the heap ever get tagged, it's even worse.
Yeah, but you're supposed to access the heap directly outside the object boundaries you allocate. So that works.
Free should be doing the right thing.
Oh yes, it's true. This is what we
Yeah,
do.
yeah,
Yes,
it's
that's
that
true.
So
Yeah.
with unwinding,
My
it's
mistake,
conceptually
check.
the same problem as should you be untagging every time you roll by?
What about unmap and then map? Does that tag? No, untag? Yeah, that's another one.
But unmap and map is just sort of giving the memory, assigning the memory space to the program. It's up to the program to
Kernel's
tag
gonna
or
zero
not.
everything, which will
But
wipe all
what if
tags.
you map it in one space, and then you unmap it, and then you map it again, but using no MTE? Does it clear out?
They're just the high
That's
bits.
another one.
They're just high bits, so the usual kernel zero clearing is going to clear all the bits for you. I'm pretty sure. There's nothing special about these bits. They're visible in the bytes.
Yeah.
So the kernel zeroing is going to wipe everything. I don't think anything special
Oh,
will
it
happen
doesn't?
there.
Okay.
Though you have to do this STG.
Hmm.
Yeah. The STG instructions to wipe out those things. Guys, we are past.
What do they do on the LLVM side of things like this? Well, okay, so I think the thing here is GCC is doing this the first time for user space. I think on the kernel side, they were using MTE, but for Android, where
Yes.
they don't run into this problem because there is no unwinding necessary in that execution model. I don't know. I'm trying to remember why is it that I came to the conclusion that this was not a problem seen earlier, because for Android kernel they were exploring they were using the LLVM toolchain to use MT instructions for the kernel.
Did they do stack tagging?
Yes. LLVM has MTE stack, MTE globals, right? Yeah.
What about a signal handler? You're inside the library with MTE enabled. Signal triggers.
Well, that's another side of things too.
right? So you're inside an MTE-enabled library. Signal comes in, you run your signal handler, which is in main application code, which is for some other library that's not MTE-enabled. And you're running the signal handler on the same stack, which is the default.
So that one should be okay, because when you, it should be okay because you undo it, as you do it and you undo it, so it's the same as a regular function call.
Yeah,
Yeah.
it's a new stack frame for the.
We don't have red zones.
I suspect that similarly the solution for exception handling will simply be to say that when you finally catch the exception, when you finally catch the exception, just memset all the memory between where the exception was caught and where it was thrown back to 0. Goodbye all the tags, and that they'd be cleared.
That's gonna have to be a special set anyways, which clears it.
I might have a question for glibc and ARM people. It's like in the description, in the documentation that we have from ARM, they define it, enabling MTE as a dynamic flag. But if you actually have a statically compiled application, then that flag doesn't exist. So which would mean that we cannot have MTE support on static linked files or binaries. So go ahead.
If you have a static position-independent executable, then you have a dynamic segment with relocation, and then you can put the dynamic tag for MTE there as well. That is, it's only if you have a position-dependent static executable that there's no direct way to store the tag, but in this case you could link an extra file that defines a symbol or something like that to just put the flag somewhere else.
Thank you.